surface, in this case with photon Doppler velocimetry, which is basically pointing a super precise speed gun at the surface. Now those vibrations revealed the structure of the interior of the sample, just as with seismology. In this way the team could infer various properties including the shear velocity and the Poisson's ratio, and these values were consistent with what we expect from superionic iron as predicted by simulations. It is worth mentioning that this experiment did not achieve the full pressure and temperature of Earth's inner core, but at the very least we seem to have produced this strange phase of matter in an iron-carbon alloy, which is an experimental validation of a mechanism that had previously existed only in simulation, and the superionic state produced exhibits strong shear softening consistent with seismic data that strengthens its viability as a candidate for the unusual squidginess of Earth's inner core. If the superionic hypothesis turned out to be true, it may help explain other things. For example, preferential flow of the interstitial carbon along Earth's rotational axis could partially account for the polar equatorial speed difference, which loosens the constraints on global lattice alignment, and the flow of this carbon may even participate in the geodynamo effect that powers Earth's magnetic field. And we should also consider this a victory for the philosophy at the heart of all of physics, that the secrets of nature are best revealed by smashing things into other things really hard. Earth's interior below us is in many ways harder to explore than the vast cosmos above. Fortunately, the secrets of both are encoded in vibrations that reach the narrow sliver of our human world from both directions, and so we build our maps for both astrophysical and geophysical spacetime. If you enjoyed this journey into the center of our planet, make sure to subscribe to the Dimksu YouTube channel and give this video a like. We bring you deep dives into the biggest mysteries of the universe every week. Let us know what you think in the comments, and we will see you in the next one. First we discovered Earth's liquid core, then we discovered a solid core within that liquid core, then we discovered that the solid core has bizarre properties that are more liquid-like. So is the inner core solid or liquid? The answer is yes. The mysteries of our own planet's interior have in many ways been harder to crack than those of the rest of the cosmos. I mean, we can send probes to the edge of the solar system, and the 46 billion light-years to the cosmic horizon are largely transparent. We can see the most distant galaxies, but the 6,400 kilometers to Earth's center are both opaque to light and far beyond the reach of any conventional drill. The best we can do is to listen to the faint rumblings of distant earthquakes and then try to piece together how those seismic waves bounce around Earth's interior to give you an idea of how seismology has lagged cosmology and the rest of physics. It was not until 1909, after Einstein's special relativity, that anyone realized that seismic waves could teach us about Earth's structure. It was Andrija Mohorovičić that noticed that some of the P waves, that's primary or pressure waves, found a shortcut from the earthquake's epicenter to seismic stations hundreds of kilometers away. He brilliantly inferred that the waves traveled through a denser and hence higher velocity region deeper in the Earth, thereby discovering the crust-mantle boundary that opened the floodgates in 1914, just a year before general relativity and the following prediction of black holes. We discovered Earth's molten core. That was by Benno Gutenberg, who found that S waves for secondary or shear were blocked across a broad shadow region on the opposite side of the planet to their origin, while the P waves could make it straight through. Shear waves only propagate through solid, so he realized that this meant there must be a liquid interior to the Earth. But even those P waves play funny around the molten core, refracting to create smaller shadow zones. Taking this game one level deeper, it was in 1936, long after we discovered the expansion of the universe and inferred the Big Bang, that Inga Lehman discovered the inner solid core. She found that some P waves did enter their shadow zones and brilliantly figured out that these must be reflecting off a solid region even deeper than the molten interior. Well, better late than never. These ideas have been refined and verified over the years, leading to our modern multi-layered model of Earth's interior. Our planet is an oblate spheroid with a low-density crust that carries slow P waves and even slower S waves, followed by a denser higher wave speed rocky mantle that slowly flows even though it is still solid, allowing it to support both wave types. Then we have the liquid outer core wreathing a solid inner core, both mostly of iron. It all hangs together neatly, explaining our dynamic planet from its volcanism to its tectonics to its magnetic field. For all intents and purposes it is right. So what do we do when new, even more refined seismic data disagrees with this model? As our seismic monitoring became more sensitive and more widespread, we started to probe the inner structure in more detail, and we started to see some glitches. For example, P waves pass through the inner core faster in the polar direction than the equatorial direction. This is typically explained by the fact that sound speed in a crystal can depend on the orientation relative to the crystal's lattice. If Earth's inner core is crystalline iron and the lattice orientation correlates with planetary spin, then the polar equatorial difference can be explained. There even seems to be an east-west hemispheric asymmetry in wave speed, and that's taken as evidence of large-scale lumpiness and/or melt regions in the inner core. One of the hardest things to explain is really deep in the weeds of the data, but it may reveal something really startling about the heart of our planet. S-waves, which are completely blocked by the molten outer core, do arise in the inner core through conversion of P-waves, and it is actually wild that we can even identify surface seismic waves that have gone through a PS then SP transition through Earth's core then back to P-waves to return to the surface, but we do find that these core shear waves travel way too slowly in that core compared to what we expect given the core's composition. Waves in the core are also losing energy much more quickly as they travel than is expected for a stiff material like crystalline iron. Now this inner core S-wave thing is a real current mystery, and to figure it out we are going to need some geophysics. There are two main ways to deform a solid: compression, expansion, so changing the volume, and that's what P-waves do, or shearing, changing the shape, and that's our S-waves. The more resistant a material is to either of these, the faster that material will propagate waves in that mode. Think about it as a more easily deformable material being sort of soft and sludgy in that mode. Crystalline iron is very stiff to both compression and shear, and so should have fast P and S waves, and Earth's core does transmit P waves as fast as we expect, but the S waves are too slow to put numbers on this. The relative shear ability to compressibility of a material is encapsulated by the Poisson's ratio, which is usually around 0.2 or 0.3 for a typical solid, but Earth's core seems to be at around 0.45, which is close to the Poisson's ratio for rubber, so not very compressible but very shearable. Let's call such a material squidgy. That's not a technical term, so do not use it on any geophysicists. So what sort of core material could be squidgy like this? Well, we are going to stick with iron in general because we know that this matches the density, and because we see that asteroids do develop these iron cores as the heavy metal drips to the center during cooling. But there are various things that could increase the core's squidginess. The first idea people had was to just add other stuff to the crystal lattice. Alloying iron crystal with hydrogen, carbon, oxygen, silicon, sulfur will significantly increase the Poisson's ratio and so lower S-wave speed, but it is now generally believed that all by itself, just alloying with any reasonable amount of these light elements, could not reduce S-wave speed by enough. Another possibility is to make the core grainy rather than one giant spherical crystal. The lattice of the core could be fragmented potentially on microscopic scales. When molten metal solidifies, its crystal lattice grows from multiple nucleation points, resulting in many misaligned sectors. Over time, these grains can merge and align to produce larger lattices or even fragment further, and it is not clear what we should expect to have happened in Earth's core because the boundaries between grains lack the strength of the pure lattice. They are more able to slide against each other, and this is greatly amplified if microscopic membranes of molten or heat-softened metal formed between those grains. This granularization and melt or premelt can potentially explain the high Poisson's ratio in the core, but the challenge with this explanation is that there is only a narrow window of grain size plus melt or premelt that gives us the right core properties to explain S-wave propagation. Push it too far and the core goes from squidgy to goopy, meaning that S-waves lose way too much energy compared to what we observe. There is also the issue that fine-grained crystal structures have a harder time organizing globally, and remember, we need some level of global lattice alignment to explain the polar versus equatorial speed difference. Most likely there is some of these granularization etc. going on, but there are strong arguments that they are not the whole explanation. We are looking for a way to retain the general rigidity of the core, potentially allowing a global crystal lattice alignment, but to still lubricate things a bit to slow down the S-waves. What we need is a new state of matter, a state of matter that allows the core to be simultaneously solid and liquid. And so let me introduce the superionic state. In this state we have a rigid crystal lattice of some element or molecule with some other atom moving freely within this structure. There are lots of examples of superionic materials with various technological applications, from batteries and fuel cells to various types of sensor. We have even observed superionic ice in which hydrogen moves freely within an oxygen lattice. In the case of Earth's core, the primary lattice would be the hexagonal lattice formed by iron alloyed with nickel. Lighter elements like hydrogen, oxygen, and most notably carbon could then live in the interstitial spaces of that lattice, moving with a freedom that is liquid-like. Now, iron does not do this in normal circumstances. At low temperature, impurities like carbon tend to stay at fixed positions in the lattice, but molecular dynamic simulations have shown that as temperatures increase, carbon atoms begin to move between interstitial sites and above a certain temperature they exhibit liquid-like behavior. According to these simulations, the high-pressure inner core of the Earth creates the perfect conditions for the iron-carbon lattice to enter this superionic state. Even better, in these simulations the alloy shows a lower shear velocity than pure iron and a Poisson's ratio of around 0.43, very close to the observed seismic properties of the real inner core. Simulations are great because they can suggest and sharpen hypotheses that we can then go and test in the real world. Now it is going to be a long time before we can access Earth's core to do direct tests, so in the meantime we need to recreate the conditions of the core in our labs, and this is where the new study comes in. This team created a hexagonal close-packed iron lattice with a small amount of carbon dissolved interstitially, then they smacked it with particles traveling at high speed to create shock pressures and corresponding temperatures high enough to unlock the superionic state. Now the theme of this episode seems to be sound speed in different materials. So fun side note, the projectile in this experiment was accelerated by a light gas gun. The projectile velocity in a firearm is constrained by the speed of sound just because a bullet is pushed out of the nozzle by expanding gas, and that expansion is limited by sound speed, but sound speed increases with molecular mass for air. That's basically dinitrogen. If instead you fill the chamber with hydrogen or helium, then a higher sound speed behind the bullet results in a faster muzzle velocity, where normal firearms can achieve muzzle velocities of Mach a few. A light gas projectile can hit Mach 20 plus or actual orbital velocities. Because of that, they are often used to study the impacts of, say, micrometeoroids on space-based hardware, but in this experiment the light gas gun is giving us a sort of particle accelerator for geology. Anyway, let's get back to the experiment. Once the superionic state was created in the iron lattice, its properties were studied similar to how we study Earth's interior by looking at vibrations on the